Hi everyone, in this video we'll try to understand how exactly Postgres implements read committed isolation level using MVCC and lock. So let's get started. So first of all, let's try to understand how Postgres prevents the dirty read problem. So for that, I'll be using two terminals. The left one will act as transaction 1, right one would act as transaction 2. So let's begin the transaction in both of them. And by the way, I'm going to use this read committed isolation level, which prevents the dirty read problem. So I've started the transaction in left and in right. So now let's say we are dealing with some users table and we want to read a user whose ID equals to 1. Right? So the username is Tom and the age is 18. Now assume that I want to update the age from 18 to 20. Right? Now let's verify whether the update is successful or not. Indeed, it was successful. But the point to note over here is we are not updating this row in place. Instead, Postgres has created a copy of this row. So this row is still present and one more copy is created, and on that copy we have updated this value, okay, from 18 to 20, right? So now if this transaction 2 tries to read the same row, let's see what would be the output. See, transaction 2 still gets this row, right? It means that it is still reading the committed row and not uncommitted row. Okay, so behind the scene, Postgres uses MVCC in order to prevent this dirty read problem. In dirty read problem, we would have read this row, right? But here we are not reading this uncommitted row. Instead, we are reading this committed row. And by the way, we would be visualizing this stuff on the Blackboard. But before that, let me show you one more demo. So in the previous demo, we saw that Postgres prevents dirty read problem, and for that it uses MVCC behind the scenes. But in this demo, we'll also observe that Postgres uses locks as well, apart from MVCC. So let's see the demo. So first of all, I'm going to start the transaction in the read committed isolation level for both of the sessions. Okay. Now in the left session, I am going to read the user with ID equals to 1, and I'll do the same thing in the right session. Okay. So for both of them, we have the same data. Now in the left session, I'm going to update the age from 20 to, let's say, 22. All right, done. Let's see whether the update was successful or not. Indeed, it was successful. Now in the right session as well, I'll try to update and see whether it will work or not. So I'm going to update the age to 29, all right? But you can clearly see that even after pressing enter, the transaction is blocked. Okay, it will be unblocked once we commit the changes over here. Once we commit this transaction over here. So let's commit this transaction. So as soon as I entered this commit, this transaction got unblocked. Why did this happen? This happened because apart from using MVCC, Postgres also uses locks. Okay, so Postgres basically uses the combination of locks and MVCC so that it can provide you different types of isolation level. In this video, we'll be focusing on read committed isolation level. All right, now let's try to visualize this on the Blackboard. All right, so now let's try to visualize both of the demos using this Blackboard. And before that, I also want to first explain some basics about how the table looks like in the Postgres database. So this is how the table looks like in Postgres database. For example, let's say I'm working with post table. So I would be having the ID, post, and likes. So these are the columns which we would be having. But apart from that, we would also have many hidden columns in Postgres. And two of them are xmin and xmax. Xmin means the ID of the transaction which has created this row, okay? And xmax means the ID of the transaction which either updated or deleted the row. Okay, so whenever we delete this row, it will not be deleted instantly. Instead, it will be marked as deleted. And in order to mark any row as deleted, here we'll write the ID of the transaction. Okay, let's say transaction ID 100 deleted this row. So here we'll write 100. And even if someone is still trying to perform an action, for example, let's say I am trying to update this row, then also we have to write the transaction ID which is trying to update this row. If you didn't get this, no worries. We'll go through this particular problem step by step. Then you'll probably get this. So let's start. So first of all, we have two transactions, transaction 73 and transaction 74. Okay. So in transaction 73, we are first trying to read the row where ID equals to 1, which is this row, right? So we'll read this particular row. Then transaction 73 is trying to update the row, right? So earlier we had 0 likes. Now we would be having 1 like. So what we are gonna do is another row would be created. Okay, so it creates this additional copy of this row, right, just for this transaction, so that it can operate or it can apply the changes which it wants. And point to note over here is, since transaction ID 73 is trying to update this row, here we have to write 73. Okay, because we have already mentioned that if any transaction ID tries to update or delete a specific row, that ID should be written over here. And in the new row, okay, in this row, we have to write 73 over here. Why? Because 73 is the transaction ID which created this row, right? That's why. And there are no transaction ID which has updated or deleted or is trying to update or delete the row. So this will be null. And apart from creating a new version of this row, it will also use lock over here on the old row. Okay, and this lock is called as row level exclusive lock. So what this lock will do is, it will not allow other transactions to perform the write operation. It will just allow them to perform the read operation. That's why in the demo number 1, we saw that second transaction was able to perform that select query. And in demo number 2, we saw that second transaction was not allowed to perform the update query, right? That is because of this lock. We have this lock on this particular row. Now obviously we would be updating the like count. Okay, so from 0 it will go to 1. Now the next step is, this transaction 74 tries to read the row where ID equals to 1. Now the main problem over here is, if you notice this much part, then you would be seeing that there are 2 rows with the same ID. So which one should you read? Should you read this one or should you read this one? So in order to decide that, we need to perform some visibility check. And in order to do visibility check, Postgres uses snapshot. So the snapshot will have 3 details. First is lowest transaction ID, which is not yet completed. Second is future transaction ID. And the third is in progress transactions. So currently there are 2 transactions which are in progress, 73 and 74. And if there are more transactions which are in progress, then we'll note them also over here in this array. Then this future transaction ID is the ID which the new transaction would get. So over here, we see that there are 2 transactions which are currently in progress. But in future, if one more transaction is going to start, then that transaction will get ID number 75. Why? Because all the transactions are monotonically increasing. Okay, like 73, then 74, then 75, 76, so on and so forth. So that's why the future transaction ID is 75. And by the way, these naming conventions are not the technical naming conventions. Instead, I have made them simpler just for understanding purpose. And also I'm not involving math over here, because if you notice, we are using this integers, and integers has some limit. For example, 2 to the power 32. So if you cross 2 to the power 32, then again we have to reset to 0. So I am not involving math in this particular video. You can just assume that all these numbers can go up to infinity. All right. Then the third detail is lowest transaction ID which is not yet finished. We are noting down this particular stuff because if I know the transaction ID which is not yet finished and it is lowest, it means that all the transactions which are less than 73 are already completed, right? So within, you can say O of 1, I can know whether a particular transaction is completed or not, right? And by the way, focus on the word completed. I'm not saying committed. Now focus on this query. So when you run this query, we'll see which row should be shown to the user. Should it be this or should it be this? So over here, we'll check two things. First is xmin should be committed and xmax should not be committed. All right. So first of all, let's talk about this row. So here 73 should be committed, but the snapshot is saying that 73 is in progress. It means that this row should not be visible to the user. Now let's go to this row. Again, here also 72 should be committed. So let's see the snapshot. So over here we can see that 73 is the lowest transaction ID which is not yet finished. It means that all the transaction IDs which are less than 73 are already finished, right? It means that 72 is finished, but still we cannot say that it is committed, right? It is finished. It can be aborted as well. So for that, we refer this PG exact table wherein we see the status of that transaction. So over here we can see the status of transaction 72 is committed. So here xmin is committed. Okay, so one check is done. Now the second check is xmax should not be committed. So over here 73 is not yet committed, right? The snapshot says that it is in progress. So both of the constraints are valid. So in such scenario, we would be showing this particular row. Okay, that is, this row would be visible to the user or to the transaction. All right. So this is how the Postgres uses MVCC. So by the way, MVCC has two things. First is snapshot, and second is using one more copy of the row so that we can perform the update in the separate copy. Okay, so it uses this MVCC plus it also uses this lock so that other transaction cannot update simultaneously. Okay, they will be blocked as we saw in the demo number 2, right? So over here, you would still get the old row. Okay, you would not get the row which was updated by this particular transaction, right? So this is how it prevents dirty deed problem. So I hope now you understood how exactly Postgres uses MVCC and lock in order to implement read committed isolation level. If you did, then please hit the like button so that this video can reach to more and more people. Thanks for watching.